What's up, nerds? This is my broken oscilloscope. And to show you that, I'm gonna hook up a channel to the test generator to get a nice clean square wave. And as you can see, none of the knobs work. If I squeeze the shit out of this thing with my left hand and use my right hand to make an adjustment, sometimes I can get it to work. Other than that, it's toast. I bought it probably 3 or 4 years ago for about 200 bucks, straight from China.
China.
But it's broken now, and I don't have the budget to go buy the oscilloscope I use at work. It's the Tektronix 2 Series MSO. So until that happens, I'm stuck with China here. We're gonna fix it. Let's get to it. I guess there's a big oscilloscope community out there that likes to reverse engineer these things and hack them, which is good for me because I was able to find the schematics fairly easily. Now you don't need to understand the schematics to follow along with this video, but I'll just give you a quick overview. This is a page from the schematics. It's the page that details the buttons and the encoders. This section is all the soft buttons. This one over here is the counter circuitry, and down here is what we're really interested in. These are all the encoders, and you can see the data lines for the encoders are all tied to a single bus. When an encoder breaks, it brings down the bus with it, and thus all the encoders don't work. So all we have to do is find the broken encoder and replace it with the new one, and we should be good to go. I'll leave a link down below in the description if you want to take a look at these schematics. I can't speak for their accuracy, but from what I could tell, they looked pretty good. In order to find and fix the broken encoder, we have to take the oscilloscope apart. So the first thing we're going to do is remove 4 Phillips screws on the exterior of the oscilloscope. 2 are located at the feet and 2 are hidden behind the handle. I thought they were being sneaky. After removing those 4 screws, the rear plastic shrouding should just come right off, exposing some of the internals of the device. Now the goal here is to get access to the PCB that contains the encoders and the buttons, and that's situated behind the front panel of the oscilloscope. So even though we've got the back shroud off, we have to go deeper. There's about 7 or 8 more Phillips screws we're gonna take out. Once those are removed, we can pull off another shroud that was hiding 2 more screws. We'll go ahead and remove those 2 remaining screws, and then we'll turn the oscilloscope around and start pulling off all of the knobs that are connected to the encoders. And this is gonna allow us to separate the front from the back of the device. And as you can see, there's just 2 ribbon cables now connecting the front to the oscilloscope. Really, we only have to remove the ribbon cable that's going to the PCB with the encoders and the buttons on it. So to remove the ribbon cable, there's a couple of locking tabs that you just have to pry open. Here, I'm just using like a plastic rod. So push those open, remove the tape, and you can gingerly remove the ribbon cable. The screen itself can just pop right off the plastic shroud. Once the ribbon cable's been removed and that front panel is pulled apart, we now have access to the PCB with the encoders on it. There's 5 more Phillips screws holding this PCB to the enclosure, so we'll go ahead and remove those and we can pull the PCB right out. See the fully exposed encoders and buttons. To determine which encoder has gone bad, we're going to use a multimeter to measure the resistance between several of the contacts on each encoder with respect to ground. So we'll take the multimeter, set to ohms of course, we'll find a good ground reference point. I found that any of the screw holes works pretty well, it's got a ton of surface area to probe, and they're all connected to ground. Each encoder has 2 mechanical mounting posts and 3 data pins. I just call them data pins. The data sheet refers to them as A, B, and C, C being common, A and B being the signal outputs. What we're gonna do is we're gonna measure each of these 3 pins with respect to ground. What we're looking for is any erratic behavior or short circuits. Now, I don't know what the correct figure should be. I'm just banking on most of the encoders working, and whichever the broken one is should be pretty apparent. This first encoder I'm measuring is showing resistance values in the giga-ohms, so for all intensive purposes, it's an open circuit. I'm just gonna take these measurements across all encoders and see if there's anything that looks out of order. On the second encoder, the middle pin was reading somewhere around 80 kilo-ohms, and all the other encoders were reading in the giga-ohms range. To me, that is a huge red flag. I'm gonna mark this one as being a bad encoder. Keep in mind that this middle pin is the common pin, and it's not actually connected to the bus that we saw earlier in the video. However, this encoder looked so out of place and such a bad measurement that I decided to replace it anyways. So I removed this encoder using solder wick and a whole bunch of flux. I used a Weller soldering iron set to 750 degrees Fahrenheit. It took quite a long time to get this thing removed. Could just be that I'm not good at soldering or desoldering, but it took me a while. And after I removed it, I decided to test this out. Word of caution, testing out like this can be dangerous because we're running 110 volts AC from the wall directly to this device that no longer has an enclosure around it. So you could get electrocuted. But after plugging everything back in and turning it on, everything appeared to work for this first couple of minutes. And then after that, all of the same issues occurred, which meant there was still a broken encoder somewhere on this PCB. So it's back to the ohm meter. When pinning out the remaining encoders, I did see some erratic behavior. If you remember earlier in the video, if I was squeezed the oscilloscope, I could get it to work. So if I started to flex the circuit board or play around with the encoders in any way, then I could get some really erratic measurements on this middle encoder shown here. In comparing the feel of the encoder to the other ones, it did feel like there was a lot more play in it. So I decided to remove and replace this one as well. Once again, tons of solder wick and copious amounts of flux. And probably about 15 to 20 minutes later, I had the encoder removed and had the test configuration set up again. After booting it up, everything worked like a charm. So in my case, it wasn't one encoder that was bad, but most likely two of them. I'm starting to wonder if the first encoder I removed, the one with the bad common pin measurement, I'm starting to wonder if that one wasn't actually broken, but I'd rather just buy a new one, just to be on the safe side. So now it was time to order the new encoders. On our oscilloscope, there's 3 different kinds of knobs. The first is the voltage per division knob, and I'm using knob and encoder interchangeably. This knob has physical clicks at each turn. I think the technical term for that is detent. So it's got several detents with it. This knob in particular does not have a center push button like some of the other ones. So I'll throw the part number on the screen here, and I'll also leave a link to the DigiKey website part in the description below. The second type of knob is the seconds per division. Now this knob also has numerous detents, and it also has a center push button, so it's got a slightly different part number. Once again, I'll throw that up on the screen here and leave a link to the DigiKey website down below. The third and final knob type is going to be what I call the smaller knobs. There are 5 of them on the oscilloscope. So they're for things like the horizontal position adjustment, vertical position adjustment, trigger level, and your V0 adjustment knob. So what you're gonna do is, after taking all your measurements and figuring out which encoder is bad, multiple encoders in my case, you're just gonna order the appropriate replacement parts. And then we'll solder the replacement parts back onto the PCB, reassemble everything, and you'll be good to go. Easy. So I've got the new knobs in from DigiKey. I'm just gonna do a quick fit check, make sure everything looks kosher, and then I'll go ahead and solder them back onto the PCB. When I solder, I prefer to use water-soluble tack flux. I like the tackiness aspect for small surface mount components, and the water soluble part is great too, because I hate when there's sticky residue left over on the PCB. It just drives my OCD crazy. And if you don't use water soluble, then you need really harsh chemicals to remove any residue left over. And for DIY stuff, I don't want to have to deal with those chemicals. The particular solder I use too is from Kester. The flux inside it is also water soluble. I'm gonna hit the mechanical mounting posts first, applying a liberal amount of both flux and solder. Next, I'll move on to the push button pins. This particular encoder does have that push button functionality, so there are 2 more pins than what I described earlier. So we'll go ahead and get those squared away. And then I'll move on to the 3 data pins, the A, the B, and the C, the common pin. Once all the soldering's done, I'll take a soft bristle toothbrush and I'll run the PCB under some pretty hot water. And I'll just try to clean off all the residue on both the front side and the back side of the PCB. After giving it some time to dry, I'll put it under the microscope and just inspect the solder joints. The particular solder I use is leaded, which leads to some nice shiny joints, and everything looks pretty damn good, if I do say so myself. Next, I'll test the new encoders out without the exterior enclosure, and everything seems to be working well. At this point, we can just start reassembling everything. Essentially, you just follow the disassembly process in reverse. Even though this oscilloscope is straight from China, I'm pretty impressed with the build quality. It's a good little scope. It does everything I need it to for my little DIY projects. Okay, so now that everything is put back together, we'll do a final test. Everything is checking out. So to sum up the video, the knobs were not working before. In my case, 2 encoders were bad, and they were bringing down the whole encoder bus, causing all of them not to work. So all I had to do was determine which encoders were faulty, buy the replacement parts, install them, and now we're good to go. So thanks for watching. Hopefully this video helps you. I know there's other videos just like this one out on the internet, but they didn't go into as much detail, and it gives me good practice with filming and editing things. And if anyone knows anything about these oscilloscope hacker communities, let us know in the description below. I'd be interested in finding out a little bit more about them.